very good morning to all for those who are in the European region and for those who are in the same region as I am, Asia. Very good afternoon to you. So today I'll be talking about using ESD simulation to model the simulator, the test setup and device under test. We will also look at how ESD indirect discharge effects are coupled into the harness, and in particular for this case, the coupling, how it affects the system. I will also show you how the use of these 3D field visualizations help in identifying the problem, and with that coming out with solutions and also evaluating the effectiveness of each proposals. Before I do so, I would like to give a brief overview of Continental. So for those who are not aware of Continental, it started in 1871 with its headquarters in Hanover, Germany. There are around 600 sites in 60 locations, employing over 250,000 people. Our technology, systems and service solutions makes mobility and transport not just more sustainable, but also safer, comfortable and personalized. As an automotive supplier industrial partner, we offer solutions that not only protects people's life and health, but most importantly, the environment. We also give individuals the opportunities to shape their own future. On the left-hand side that you see here, Continental is having three group sectors: the automotive technologies, the rubber technologies, and the powertrain technologies. So under the automotive technologies, there are two main groups: the autonomous mobility and safety, followed by the VNI, which stands for vehicle networking and information. This is where I'm working in. Under the rubber technologies, there are two groups, which are the tires and ContiTech. Lastly, we have the Vistesco, which is the business area which concentrates on the know-how for how efficient driving, the evolution of future powertrains. Coming to Asia, Singapore, for those who have not been to Singapore, in Continental itself, there is two entities. One in the northern side here, which is the ContiTech Twin Services Private Limited. So they are mainly focusing on the production of conveyor belt system, elastomer sheeting and suspensions, vibration systems. Then at the southern part of Singapore, which is near the Marina Bay Sands area and Marina Gardens, are basically the tourist hotspots. You'll find the rest of the other 5 entities. So we have around 27,000 square meters of area, housed under 3 buildings that you see on this picture here. And in these buildings, we have around more than 1,400 headcounts. So going a bit more in depth, in Singapore itself, we have various product groups or business units. VNI itself contains 3 business units. One, the HMI, the CCN, which stands for Connected Car Networking, and also Central Engineering. Lastly, the Commercial Vehicle and After Services. We also have this HEAT, which stands for Holistic Engineering and Technologies. They are mainly responsible for translating friction to science. They are also the main enablers working on future topics such as smart city, AI applications, and also cybersecurity. Each BU itself, business units, has its own responsible product area, but at the same time, we work together with other business units towards a vision of a holistically networked vehicle that is always on. So having this introduction on the company, I'll go into the technical topic for today. So as we know, ESD itself is the sudden and momentary flow of electric current between 2 objects when they have different electrical potentials. The arcing happens when by either contact or electrostatic induced effects. As we know nowadays, the electronics are getting faster, so these devices are required to work with a lower power consumption, higher integration density. So what we are expecting nowadays is the reduction in junction sizes and the oxide thickness. So this coupled together means that they are even more susceptible to ESD events. To put it in another scenario that is more relevant to you would be the case where you would touch a door in Europe and you will feel a spark. So I will also relate it in another more comical way, which I think is more makes a better impression. So ESD events happens in many scenarios. So one way is also when this triboric effect separates the charges, and when they're brought together again, you will see sparks happening. And when ESD happens, the effect will be as follows. You will see software upsets whereby the data is corrupted. You can also see latent effects which are built up over time. And all these latent effects are unpredictable. The worst is when catastrophic failure happens, and this is when the device is permanently damaged. You will see probably under the X-rays or microscope burn through within the semiconductor devices or even passive components. Now, the motivation here, why do we do ESD modeling and simulation? The reason is simple. Firstly, we can measure or so-called measure these voltages that are induced on the traces and current and cables during this so-called ESD event. Inside the simulation environment, we can place almost infinite number of probes to monitor different parts of the PCB or even the setup. Secondly, it is possible to visualize all these field propagations or currents that is moving around the simulation environment. Lastly, it gives us a better insight of the whole system behavior from the physical point of view with these field propagations and also the measurements of the voltage on these signal lines that we are looking at. However, there are certain limitations to simulation and modeling. They do not tell us whether the impact is affected. So what I'm trying to say is that, for example, if there's a glitch on the signal, it doesn't mean that you will see a display upset, for example, or you will not see a sudden hanging in the system. So it also does not tell us whether there's a okay or not okay, which means that, for example, the device will be damaged or not on the long run. However, with simulation modeling, it gives us the advantage of what I mentioned in the first point. We are able to measure all this, which sometimes in real world, it is quite challenging to do the measurements, especially in the lab where you have only limited time to do the testing. So basically for us working in the automotive environment, we are following this ISO 10605 standards. The objective is to carry out tests to simulate an ESD event that happens into the vehicle electrical system based on this human ESD model. So basically these are the ESD generator characteristics whereby you have the output voltages ranging from 2 to 15 kV or 2 to 25 kilovolts depending on the type of contact or air discharge. Contact discharge itself means that the tip of the ESD generator is brought in contact with the DUT before the discharge switch is actuated. On the other hand, air discharge is the process whereby the discharge switch is already turned on, and then the gun or the tip is brought with a demander speed close to the DUT, and through the dielectric breakdown, the arcing happens. Under this scenario, we also have different RC requirements depending on the scenario that we want to simulate or emulate. Firstly, for the storage capacitance, there's 150 or 330 picofarads. So it is trying to simulate the scenario whereby you are touching the component from outside the vehicle or within the vehicle. Secondly, we also have this discharge resistance, either 330 ohms or 2000 ohms. This will be the scenario emulating whereby the contact is through a metallic part, for example, a key, a ring, a pen, for example, or screwdriver. And then for the 2000 ohms, it will be a human body through the skin. So the picture below that you see is the typical setup when we try to do a ESD testing based on the power up mode. So contact discharge can be either applied onto the pins of the DUT through the harness where it is exposed, or air discharge perhaps to the back or the front of the DUT through the screen. So under this 10605 standards based on the 2008 edition, there's also an additional approach for the ESD power-up test. The intention is to produce a more repeatable test results to better correlate with vehicle-level ESD tests under the real-world environment. That means what it's trying to do here is trying to emulate the scenario whereby the contact is on perhaps the car body, and then this discharge happening and coupling onto the harnesses within the vehicle onto the DUT itself. So under this test setup, you can see here, these are the different views from the top, the side, and the other two planes that have been coupled together to form this, or joined together to form this coupling plane. So this field coupling plane is at least 10 mm wide. It's at least 10 mm larger than the DUT when it's placed here. And then for this thin strip that you see here, it must be at least perhaps 40 mm to support the whole harness. And points number 3 are the islands which the discharge will be done. So this plane can be either constructed using copper or brass. So moving on, I will talk about this ESD gun setup. So this gun is being borrowed from the paper that you've seen below. So there are some adaptations inside the excitation method, as numerically it is not possible to simulate a relay that operates within a few picoseconds apart to allow the current to be discharged in. So for more details on how the author adapts the RC networks and the port excitation to reproduce the slow charging and the rapid discharge, you can refer to the paper below. However, as this model has already been correlated with another gun, I would take this as quite a good chance to use it. And most importantly, the key points is that the accuracy of the first peak and the reproducibility of the second peak is almost there, as been validated by the author. So there are also various ways to emulate this gun. Either you can use a simple circuit model inside the design studio, or you can use this simplified gun model, or perhaps even a more complex models whereby the harness is being modeled in detail. For this gun, as it was not modeled by me, so I will need to do some form of calibration to better understand and also make sure to ensure that this behavior is as according to the standards. So inside the standards, there's also this simulator verification setup where under different voltage excitation, you will see that the peak current will vary accordingly, and there's some tolerance to it. Then under a 4 kV excitation, they will measure this current, whereby it is, or the peak of the current will reach a rise time of 0.7 to 1 nanoseconds during the first peak, and also the RC discharging constant at the back. And you can see from this image here, for this test setup, there's a metal plane approximately at least 1.2 meters high and wide. The objective is to shield the oscilloscope from the indirect coupling of the fuse. So moving on, you can see these waveforms here, the current profiles that are being excited inside the simulation with the gun, and also just now the test table that you saw earlier on that is 1.2 meters wide and high. So from here, I did measurements to so-called correlate the current and also the rise time as specified in the specs. So basically, you can see that the relationships is quite similar. Next, I will move into detail on how the PCB is being modeled. But before I do so, this is the front view of the PCB. So for this product, it is basically a central input device, which is housed in the center of the vehicle. So what it does is that it collects information either from the cluster or from certain video input, and then there are touch features on it. So on this PCB, you will see that on this section here, you have the automotive controller, serializer here. Okay. The objective for this serializer is to provide information to the display that you see the slot here. And being a central input device, there are touch controllers for the touch button to be interfaced to the outside and also to the display. So this display itself comes with touch features, and the rest of the ICs that you've seen in these regions, okay, are the power supplies, mainly the power regulation SMPS, such as for the 5 volt, 3.3 volt, 1.8, and also the boost regulator for the backlight. So the region that you see here is where the main connector is. So this is the back view of the PCB. So similarly, you can see here now is that you have the lines here connecting to the display interface. These are the touch sensor lines, and on the right hand side, you have the OLDI lines, which are the so-called open LVDS signals. They are providing the information to the display interface, mainly for the graphics showing on the display. So this is the 3D model of the PCB that you see here. So basically all the components, mainly the passive components, are mounted in this model. And to simplify or to minimize the complexity of the model, only the power, ground, OLDI lines were modeled. The reason for doing so is because during one of the ESD tests, there was a flicker on the display. So the reason, what they are doing is that they believe that this problem was caused by the OLDI lines or the display interface lines that you see here. So we did a so-called mock-up whereby on these lines here, you can see there are no ground vias. Okay, as we know that to ensure good signal integrity, usually you have these grounding vias besides it to serve as a good return path. So through these models, they are also trying to study what happens when you have all these solutions to improve the design. In addition to those passive components here, there are also other active components, for example, like the diodes or the transistors modeled using a short. The reason for doing so is because there are certain power lines on it that has transistors onto it to act as a switch. So to remove the complexity or to simplify it, all these are being assumed whereby the switches are turned on, allowing the voltage to be inside to activate the different parts of the PCB. So moving on, this is the behind view or the rear view where you will see that you have ports being placed here, okay, to monitor the signals for the clock, the 3-volt tree here, and also before the filter and after the filter, okay, for the display lines. So once the gun and the PCB model is available, the next thing that needs to be assembled is the setup. So for this setup, you can see it is the whole table, okay, with the coupling strip. So just to share with this project is that there are actually 3 different CST projects made available. One is the PCB model, the next is the gun, the last is the table. So all these are snapped in easily using anchor points. So this means that it is possible to replicate the same problem or the same setup for other projects again. So basically for this test, the RC networks that was being applied is 330 ohms and 330 picofarad. So this, as I mentioned earlier on, this was a central input device that was placed in the middle. So the assumption is that the device or the DUT can only be accessed within the vehicle. This is why these values are selected, and also based on the 15 kV excitation, which is the maximum level what we are testing. There are also certain modifications to the whole setup. So 2 modifications is that the ground, okay, this is supposed to be interfaced to a liaison and then to a test box. However, for this case, these are removed and then the grounds are being connected to the table here. Secondly, the ground strap that you see here is supposed to be placed at the bottom here, near the end of the plane, of this strip coupling plane. However, to simplify the whole model, so it was assumed that this current will be will be returned to this path here. And the whole harness that you see, if I miss explaining the setup, each islands are spaced 50 cm apart, half a meter apart. So if you have 3 islands, you can see that the whole length is around 1.5 meters, and then a harness length of approximately 30 cm away. So based on the standard, the harness standard length is supposed to be 1.7 meters long, having a tolerance of 30 cm. So this will be the 4 permutations that are being carried out. So to study 2 things. One, the PCB variation. So inside these 2 models, one has the ground vias at the OLDI lines, the other one doesn't have it. And then for the second case is to simulate the gun where it's placed furthest away from the island, on the island furthest away from the DUT, and the island that is closest to the DUT. So these 4 permutations were being studied initially. So looking at these figures, this was the scenario whereby the original design with the ESD pulse at island 3, which is the furthest away from the DUT. So looking at here, you can see that there's a significant amount of coupling onto the LVDS lines. Secondly, for the power supply lines, which is a 3-volt tree, you can see it is relatively small. The power sweep for the line for the coupling noise on the clock line is approximately 360 millivolts and a width of 15 nanoseconds. If I move on to the next scenario, you will see that the coupling voltage now has slightly reduced to around 320 volts, and most importantly, the width is being changed from previously 15 nanoseconds to 8. So this gives a good idea whereby the distance between the coupling or the excitation point has impact only on the pulse width, but not the maximum coupling voltage level. This is probably like a crosstalk effect whereby the coupling voltage remains the same, I would say saturated. However, when the coupling length changes, then the pulse width would varies accordingly. So the next one, you will see that is the one that has the modified designs whereby the ground vias are being removed. So from this results, you will see that it will be similar to what we have in case 1 when the excitation is 1.5 meter away from the DUT. Now, looking at this, I guess I probably have two conclusions here. One is that you can see that ground vias, whether it is there or not, it doesn't help in removing the noise that is being coupled onto the LVDS lines. Secondly, placing the two probes there have some impact. The difference between the two is that the 3V3 display and the 3V3G are before and after a filter. So you can see that the level before and after has been reduced. However, the reduction is considered almost negligibly small. So this doesn't also provide insights to where the problem was. So it'll be interesting now because for the next slide, I will show you the placement of these field probes and also the field monitors to see the different effects. So now you can see these are field probes being placed at the coupling strip at the different islands, and also some field probes are being placed before and after the PCB. Okay, this will be a relative distance here. So if you look at the energy of these three field probes here, I only circled these two to make it simpler to digest. You can see that the coupling of energy at the low frequency is almost similar. However, as the frequency increases, it is observed that the energy coupled on the PCB is larger than initially. So you can see this on the green line as compared to the blue and the brown lines. So as the frequency increases, you can see these levels of energy coupled onto the harness going into the PCB is higher than before. However, if we were to look at the field probes that are being placed behind the PCB now, you will see that there's a substantial decrease by around 15 dB. So this means that most of the energy actually are coupled onto the harness and going into the PCB. And perhaps this radiation effect does not occur on the other side. Most likely is because the PCB itself is a 4-layer board. There's a solid ground plane in the middle layer, inner layers. So this probably acts as a good shield against it. Looking at the field probes, it also doesn't provide much insights into the problem. So we can place field monitors to look at the return or the flow of the fields at different frequencies. So at the lower frequencies, for example, 100 megahertz, what you observe is that when the first excitation is happening, you will see the current moving forward and then returning back through the shortest path to the ground at this and this region. This will be interesting because you will see that most of the energy, as shown using the field probes earlier on, they are all on the coupling strip. And then once it crosses over, okay, after the PCB, you do not see substantial energy on the other side. So if I were to move to another frequency, which is 0.5 gigahertz, 500 megahertz, you'll start to see all these standing modes coming in because of the frequency that you are using. You will see that these wavelengths correspond to the frequency here, and also what will be interesting now is that rather than having all these field propagations around the edges of the PCB, I hope you have observed by now there are a certain region inside the PCB here that has these hotspots on. So now this visualizations actually provides more insights into the problem. So with this, I started to zoom or investigate it even deeper into why this coupling happens. Okay, so if I were to change the axis now in this plane, you will see that the harness is at the back here, this strip here, and this is where the gun is. So when the excitation is on the connector side, you will see that this energy actually couples onto this part of the PCB into the LVDS area, which is a serializer that I mentioned earlier on. So initially, when we thought that the problem was due to signal integrity, it might not seem the case, because if we are to investigate even further, these lines are actually the power lines providing power to this IC here. So to put it simply, this region is always in the hotspot, and it also gives a deeper insight or a better direction into where the problem is now. So to make it more complete, I also showed a few plots at 1 gigahertz. So basically what it is trying to show here is that at this frequency, the return current would choose to flow back along the path of the least impedance, as what we have always understand. So moving on, I will show the schematic of this problem here, of this DUT here. So basically, this is the connector where the power supply line comes in, and this is the ground. So when the power supply line comes in, this switch is turned on, enabling the voltage to be sent to various parts of the regulator IC. So all these points, although I already know where the hotspot is, okay, but I still place some voltage probe there to measure and quantify how much difference between these two ICs are, or the three ICs are. So now the model that you see here has been adapted with the identification of the cause of the problem. So this time around, voltage probes are being placed to monitor the noise when the ESD pulse is excited on the setup. So the probes are being placed in these two regions here on the other side of the board, which is near the touch IC, and then on the other side, which you saw earlier on, which has the hotspots on the display IC or the serializer. So interestingly, compared to other ports now, okay, or other places of the PCB, there's relatively low levels of coupling noise in. However, on this line, which is IC 1500 pin 4, you will see that when the ESD discharge of 15 kV into the unit, there's around 18 volts of noise being coupled inside. Most interestingly, if I were to place and mark out these two peaks, okay, you can work out the period to be around 2 to 3 nanoseconds. So this coincides with the resonance frequency that you saw earlier on at around 500 megahertz. So now going back, actually for this IC here that you saw, there's actually a filter being placed there, which is the one that you see here. Okay, but from the schematic, it's not shown here. But most importantly is that when we have these filters, okay, placed on this side, which is near to the connector, okay, these two ICs that you see here do not observe the coupled noise, whereas for this IC, with the placement of the filter close to it, it seems that it is not effective. So this comes to another advantage of using CST. I do not need to wait for the layouter, for example, to make changes inside. So once I've come up with some conceptualizations of ideas to improve the design, this can be done easily within CST Studio Suite itself, either using PCB Studio or CST Full Wave Microwave Studio. So what happens here is that you can see on this connector pin now, okay, this strip is being exposed. So they are being cut up like what we do in troubleshooting, however, inside a virtual environment. So by removing these two strips and then placing two ports here, it is possible to add in the filters that was mentioned earlier on. Okay, so with this addition of two ports, you can add in the spice models and even create a lump circuit element to model the big inductor that was around 22 microfarads. 22 microhenries inside. So going back to the same model again, by rerunning it again, you will start to see that once the filter is placed close to the connector, okay, the hotspot is now suppressed. So the hotspot that was seen earlier on in this portion has been so-called significantly reduced. So moving on, it is not just possible to do one simulation. It is also possible to have some certain optimizations now. So various filters configurations are being played with. For example, as mentioned earlier on, at the schematic level, there's already capacitors placed nearby. So I played with different values such as placing only an inductor, placing additional LC circuit filter, a capacitor and an inductor configuration, and also most importantly a pi filter. So you can see that the effectiveness of different filter solutions can be studied easily, and then based on this optimization, you can derive what will be the suitable value to be used or even the layout change to be made to suppress the problem you're seeing on the PCB. So with that, I come to the conclusion of the presentation. So looking at the simulation results for the two different PCB layouts, it can be concluded that the placement of the stitching vias has no effect on the coupling level for this design. I think most importantly, the level of common mode noise is relatively substantial. So I would guess that since it is a differential signal, most likely it will have almost maybe insignificant impact on the design. However, on my side, I guess investigation should be carried out to ensure that this has no substantial corresponding signal integrity impact. Next, the problem initially been so-called the solution that was being defined using the vias was not the actual solution. So to better understand the problem, 3D field plots and even the field monitors has to come into play. This will definitely help in analyzing and identify the problems. So through the use of CST, as shown earlier on, it was possible to carry out various what-if analysis to derive a suitable solution to solve the problem. Before I conclude my sharing, I'd like to say that when good practices come to fail, the only way to separate the myth from reality is to put it to numbers, as shown previously, through the implementation of different filters and then re-simulating it again. Lastly, as this ESD simulation was carried out in a virtual environment, so no capacitors or components were damaged in the process for ensuring ESD compliance through the simulations. So I thank you for your time, and most importantly, I would like to thank the colleagues or the guys from Simula, Sophia, Vanessa, and Awan for making this webinar a success or possible. Thank you.